Hi, everybody. This is Jim Corkins again, and we are starting a new module, and it's about forces and Newton's laws. So please do the reading. It really will help you on this. Okay, so we all, or most of us, have probably heard about Newton's laws, and we might even know the specifics. The number of them doesn't really matter too much. What is important is they are highly predictive concepts. Okay, the term laws should be interpreted loosely. They're theories, just like everything is in science. The first one being that every object at rest maintains will stay at rest until acted upon by an outside force. If that object is moving, it will be moving in a straight line and continually moving in that straight line at a constant velocity until acted upon by an outside force. This law is often referred to as the law of inertia. And we'll get into the concept of inertia and how it relates to this law. The second law refers to basically the mathematical relationship between force, mass, and acceleration. Prior to this moment, we have been basically referring to acceleration as a force, or really been talking about it as acceleration is coming from a force. Okay? But now what we have to do is think about the mass of the object as well. Okay? So acceleration isn't exactly the same thing as a force. In fact, force is equal to mass times acceleration. And so dividing both sides by m, what we get is a relationship between force, acceleration, and mass. Okay? And we'll get into that in a few moments as well. The final one, which I think is really strange, but it is predictive. Whenever one object exerts force on another object, that other object exerts the exact same force back on the other object, but in the opposite direction. So forces are equal and opposite. Okay? And so it's often called action-reaction pairs, right? So we will also get into that as well. All right. Moving on. When we're looking at, when we're talking about Newton's first law of motion, we often refer to it as inertia. Okay. Basically, it's the tendency of an object to continue its current state of motion or lack thereof. Okay. And if you need to change its motion, you have to exert a force on it. So the concept of inertia is basically an object's tendency to resist change in its current state of motion. Okay? Basically, mass is inertia. Any object that has mass has inertia. Okay? Now, mass is independent of gravity, in a matter of speaking. For example, your weight is not equal to inertia. Weight is equal to your mass times whatever gravitational field that you're in this case, 9.8 meters per second squared. Okay? So if you were floating in outer space, away from any planets, where no gravitational field was around you, you would have mass, but you would not have any weight. Okay. Now, again, mass, which is measured in kilograms, is what inertia essentially comes from. Okay. The larger your mass, the larger your inertia. So it's much more difficult to get a bus moving than it is a sports car, right? So if you've ever had to push cars that have broken down, you kind of know what I'm talking about. So whenever I see a big truck that needs some help and I run up to help it, I know it's going to be a little bit more difficult than pushing a car. Okay, so that is the real quick understanding of Newton's first law. Again, please read your book because it does go a little bit more into depth. But given that you now know that an object with mass will resist changing its motion, let's investigate your current conceptions about Newton's first law. Okay? So suppose a rocket has its engines firing in space. When its engines are firing in space, its velocity will be constant, will increase for a while and then stay constant, and then its velocity it'll speed up and then stay constant, or will increase forever. So take a moment and think about this, and let me know what you think. Pause the video now. Well, in space, it's a vacuum, okay? So there is no air friction to kind of stack up and or air to kind of cause any kind of resistance. So in a vacuum, if you are moving to the right, let's say you're moving to the right here, and you also have an acceleration to the right, okay, because this acceleration is essentially because the rockets are pushing you. So now that acceleration, we're going to define a little bit differently. It's going to be equal to the force of the rockets in the x direction by the mass of the rocket. Okay, so this rocket has a mass, m sub r. Okay, and so whatever the force of that engine is, if you take that force and divide it by the mass of the rocket, that will be the rocket's acceleration. But the important point is that the object is speeding up and therefore has a velocity vector and acceleration vector pointing in the same direction. But without any resistance to stop it, it will essentially increase its speed forever. Okay, and we're considering Newtonian physics, not relativity, where eventually it hits the speed of light and a lot of crazy things happen at that point. Okay, anyways, so this is the beginning. So this object will increase forever in a situation without any resistance. Now, something slightly different. I'm going to move this over here. I'm going to bring it to the front. So I brought it to the front. Okay. Now, similar situation. You have this rocket that has a velocity vector in the x direction to the right. So it's moving to the right, but its engines aren't firing. Okay, so it's moving at a constant velocity. Okay, so if it's got a constant velocity, what force is required to maintain that constant velocity in the vacuum of space? Will it be zero? Will it be equal to the mass of the object? Will it be equal to the weight of the object? Or will it be equal to the force required to stop it? Please think about this question and pause the video now. Okay, we're back. Well, it is hard to divide Newton's three laws together, okay, or rather concepts. But a moment ago, we just talked about acceleration is basically the force in the x direction, so the engine's pushing on the rocket, divided by the rocket's mass. Okay, again, it's got a mass, m sub r. Well, if it has an acceleration of 0, which would be constant velocity, then mass cannot be 0. If something has mass, it has to be 0. That means this force has to be 0. In other words, if something is moving at constant velocity, there is no force being applied to it. It is just moving under its own inertia at a constant velocity in a straight line. So the force required to keep an object moving at constant velocity is 0. Okay? Okay. Now, we've all experienced inertia in different ways. Okay, so suppose you're at the bottom of an elevator shaft. You're in an elevator at the bottom of the building, right? And you get in and you hit the up button. When you and so the elevator's not moving, you hit the up button, and then it's a really fast elevator, and it begins moving upwards or speeding up as it's moving upwards. What would you say if you happen to be standing on a weight scale? What would your weight scale read as you're speeding up, as you're moving upwards? Would your weight scale read a higher weight than you normally are? Would your weight scale read less of a weight than you normally are? Or would it be equal to your current weight? Try this out and think about it. Pause the video. Okay, so we're right here. This little guy he's moving upwards in the positive y direction, and he's also accelerating upwards, okay, in the y direction. Okay, now his body is resisting moving, okay, and when you get into an elevator, you do feel heavier, right? You do feel heavier. Well, that would register as an actual heavier weight on a weight scale if you're standing on a weight scale in an elevator, okay? Now, there's a lot of math behind this, but basically what it is your body is not trying to change its motion. It's currently not moving. And when something begins to shove an object, in this case you, upwards, your body is going to resist that change in motion. So the bottom of the elevator is moving you upwards. You're trying to resist that change in motion. So the result is that you would feel heavier. Okay. Let's try another one. You're standing on an elevator at the top of the building and you hit the down button. And so now you are moving down in the negative y direction, and you are speeding up, so you're accelerating down. Can you remember how you feel when this is happening to you? When you're speeding up, you're at the top of an elevator shaft and you push the down button. How do you feel? Do you think the weight scale would read a heavier weight than normal, a lower weight than normal, or the same weight? Try this out. Pause the video. Okay, well, again, your body is not moving right at the top of the elevator shaft, top of the elevator, and you hit the down button. Now, what is essentially happening is the bottom of the elevator is dropping out from beneath you. So if it dropped really quickly, like faster than gravity, you would be floating in the air, and then the weight scale wouldn't be registering any weight because it would be floating right next to you. So you would be in a term called weightless, which is also in free fall, right? So if you're not accelerating at gravity or something, if you're accelerating at less than gravity, then your weight scale would read a lower weight than you normally will feel. Okay, so you do feel lighter. This is also true when you are moving upwards in an elevator and you begin slowing to a stop. Again, it depends on the direction of that acceleration vector. When you're in an elevator and you're moving upwards and the elevator is coming to a stop, you will also read a lower weight than you normally do, because now you do have a velocity, and now the bottom of the elevator isn't pushing on you anymore. It's dropping off that acceleration. So essentially the acceleration vector the bottom of the elevator is dropping off in its motion. So you'll feel lighter. Finally, let's say you've hit the button and you have been moving down at a constant velocity. Okay, so when you're moving at a constant velocity, how do you feel? Do you feel like your weight would be higher? Do you feel like your weight would be lower? Or do you feel like it would be the same? Go ahead and try this out and pause the video now. Well, when you first are moving down in an elevator, you're speeding up when you're moving downwards, right? But then something happens. You reach your maximum speed, hopefully, and the elevator now hits a constant velocity. So you're feeling lighter at first, and then all of a sudden your acceleration in the y direction is equal to 0. At that point, you will weigh what you normally weigh again. You feel lighter here, so decreases, your weight decreases. But then when you hit your constant velocity, well, if you couldn't hear anything, you wouldn't even know that you're moving. If you were just in an elevator, it'd be really hard to tell unless there were sounds that you were moving at all. So basically, it would show the same weight as you normally would do. Because in that state, when you're moving at a constant velocity, it's unclear who's moving relative to who. Are you moving? Is the building moving? If the building's moving, you're standing still, but from a different perspective, you feel like you are moving and the building is standing still. So again, it's kind of like drinking coffee. All these questions are kind of like in your car when you're drinking coffee. If you're at a stoplight and you begin to floor it, well, it's going to be dangerous to drink your coffee. Your coffee in its mug is going to not be moving, and then all of a sudden the back of the mug is going to begin pushing it and accelerating it forward. So it's not a good time to drink your coffee. When you're slamming on the brakes, your coffee is going to slush forward, right? Because it's moving at a constant velocity, and suddenly you hit the brakes, so the front of the coffee cup is pushing against your coffee, trying to slow it down. Well, here, when you hit a constant velocity, that's when it's safe to drink your coffee, because the water level is level. It's not sloshing backwards like when you're speeding up, and it's not sloshing towards you as when you're slowing down. Okay, so it would show basically a level coffee. Okay, let's move on to Newton's second law, because we kind of have already been working with it a little bit. It's kind of hard to divide these three concepts into different concepts, but basically this is the mathematical relationship between force, mass, and acceleration. And this is where the concept of weight comes from. So force is equal to mass times acceleration. So if you want to calculate somebody's weight, that's going to be equal to their mass in kilograms times gravity. So mass in kilograms times meters per second squared, well, that is called a Newton. So remember, Newtons are kilograms meters per second squared. It's a mass times an acceleration. Okay. In America, we call that Newton force pounds. But in Britain and other countries, they just refer to mass in kilograms. Okay, so we are talking about two different concepts. When they're talking about mass, we're talking about weight. It is kind of confusing, but essentially force is the mathematical relationship between mass and acceleration. And if you want to calculate somebody's acceleration, you do have to take their mass into account. Now, acceleration is directly proportional to force. Okay? If acceleration goes up, force goes up. Now, if mass increases, then your force is going to increase. Okay? The force required to accelerate it at that constant velocity will also have to increase. Okay? So, if somebody's mass isn't changing, a higher acceleration will require a higher force. Okay? But if you want somebody to maintain a constant acceleration and they have a high mass, you're going to have to increase the force on them. Now, over here, if you want to keep a constant velocity, constant force on something, and you wanted to increase acceleration, well, let's say your mass decreased. Well, your acceleration would have to increase in order to maintain a constant force. Okay? So that's kind of an interesting thing, since acceleration and mass are inversely proportional to each other. Acceleration is on a numerator, mass is on a denominator. When one goes down, the other one has to go up. Okay? So basically, if you push somebody with a force of 100 newtons and they have a low mass, they will have a higher acceleration. However, if you push somebody who has a heavy mass with the same force, they will have a lower acceleration. Okay? So let's see if you can, let's see how you've done. Okay? So 2 toy vehicles, one a sports car and another one a toy bus, both have the same engine that exerts the same force on each other. Okay? So they both floor it. Which one will be moving faster after 1 second? Go ahead and try to answer this question and pause the video now. Okay, well, again, this is basically force, the relationship of acceleration, force, and mass. The lower, so let's give a force to this. Let's call the engine, if it's a toy car, the force is going to have a force of 2 newtons. Okay, so let's say the same little toy engine has a force of 2 newtons. Well, the toy car's acceleration is going to be equal to 2 newtons divided by 1 kilogram. So its acceleration is going to be 2 meters per second squared. The car, the school bus, which has a 4 kilo, it's going to have the same engine, so it's a 2 Newton engine, but it's 4 kilograms. Okay, so that means that's 1/2. So that is going to be 1/2 meters per second squared, or 0.5. That makes more sense to write it that way. Meters per second squared. So the toy car, having 1/4 of the mass of the bus, is going to have 4 times the acceleration of the bus. Okay? So that's the relationship between force, mass, and acceleration. That's one way of thinking about it. Another way of thinking about it is this. So suppose a cart is driven by an engine and is pushing it with a constant force. Again, let's call it a 2 Newton force. Okay, and suddenly it starts draining fluid at the bottom. So it had rainwater in it. It starts draining the fluid at the bottom. When it does this, what will happen to the cart's speed? Will it speed up? Will it maintain its constant speed that is currently that it's going at, or will it slow down? Okay, so think about it for a second, and pause the video now. All right. Well, as it's draining fluid, its mass is going to be dropping. So the mass is going to be going down. And now, again, it's got a constant force working on it. So if its mass is going down, it's going to actually start increasing its speed much quicker. It's going to actually start speeding up much faster than it was prior to that. Okay? All right. Well, that was Newton's law. Newton's third law is really weird. Sometimes my brain has a hard time wrapping around it. But essentially, anytime you touch something, whether you're moving, whether they're moving, whether they're both moving together, if you push on any object to the right with a force, that same object, regardless of its mass, is going to push against you in the opposite direction, right? So when you put your hand on your table, the table is pushing up against your hand, holding it up with the same amount of force at when your hand is on that table. Otherwise your hand would break through the table, right? So, and it doesn't matter if you're moving or not. If you're moving to the right, pushing on each other, you have the same force. Now that might not translate with who will be accelerating more, because acceleration, you have to consider the masses of the objects, right? But essentially, forces are always equal and opposite. Okay, that doesn't mean the accelerations are equal and opposite. You have to think about mass when you calculate that, just like we did over here on these two things. Okay. Now, let's talk about action-reaction pairs. So a rocket engine exerts a force on hot gases, expelling them out the back of the rocket. The upward motion of the rocket is caused by the hot gases rushing out of the engine, and those hot gases, will they be pushing against the ground, pushing against the air, or exerting a force back on the rocket engine? Try to answer this question with what you think is actually happening. Pause the video now. Okay, so here is the bottom of the rocket. If the rocket is pushing, and here's some gases, okay, so we're saying this, that the rocket is going to be pushing these hot gases down, right? And so that's why they will begin moving down. So since those hot gases have a really small mass, like itty bitty little mass, when that force downwards is exerted on them, they are going to have a huge acceleration vector, because their acceleration vector is proportional to how small their masses are relative to that force. Now, those little gases also push back on the rocket with the same force. But since the rocket has a big, huge mass, its acceleration compared to the gases is going to be really small. So it's kind of weird. You have to kind of really think about this. But essentially, if the rocket pushes on the gases push back on the rocket. Okay? And so they will have the same force, however, their accelerations will be different, right? It's actually quite dangerous to stand, I think within, half a mile of a rocket taking off. I've even heard that it could actually cause severe internal injuries if you're close enough to it. That's because the gases are accelerating very quickly. The rocket, relative to those gases, is accelerating very slowly. So it's kind of weird. Its acceleration vector is not as large as the gases. Okay, let's keep moving on. Suppose a rocket has its engines firing in the vacuum of space. For the rocket to speed up, the rocket must push against space, the vacuum, or the gases. Try pausing the video now. Again, so for the rocket to accelerate, it's got to push a force on those gases. And when it does that, the gases will then push with the same force on the rocket. And that will then cause the rocket to start to create an acceleration vector and start speeding up relative to the size of its mass. These gases are going to be moving very quickly. Since they have an itty bitty little small mass, their acceleration vector is going to be huge in comparison to the rocket. Okay? So it is pushing against gases. All right. I saw this one on the internet a long time ago, a couple months ago, and I thought it was a really cool problem, although I had done this problem in the 90s. In fact, these slides are slides from the 90s. God, I'm getting old. Okay. Anyways, suppose you had a spring scale, and it wasn't tied to anything. It wasn't being held by the table, and you've tied a weight on one side of that scale of 5 newtons, and you tied a weight on the other side of the spring scale. And when you pull either side of a spring scale, it's going to read a force at the center of this. The question is if this is exerting a 5 Newton force to the right, and this is exerting a 5 Newton force to the left, what will the spring scale be reading? Will it be reading 5 newtons, or 10 newtons, or 0 newtons? What will the spring scale be reading? 5 newtons, 10 newtons, or 0 newtons? Think about it and pause the video. Okay, well, here's what I like to think about. Let's suppose this was just for a moment hooked to a wall, right? It was just connected to a wall, and you connected this side right here to a wall, okay? And then you hook this up to a spring scale. And when you do, that spring scale is going to read 5 newtons, okay? Now, there is no difference from a wall holding this side still versus an equal amount of force on this other side. So this is going to be pulling down 5 newtons here, and this is going to be pulling down 5 newtons here. Now, a lot of us will think, oh yeah, well that should be either reading 10 newtons or 0 newtons. But really, this weight in this situation is just holding this side still while this other one is pulling down on it. So it will also read 5 newtons as a weight scale. Okay? Because the forces are equal and opposite. If this is pulling down at 5 newtons, this has to be pulling down in 5 newtons. So the weight scale is only going to read a 5 Newton force acting on it. Okay? Interesting thing though, since this is pulling down at 5 newtons, this is going to be pulling to the right at 5 newtons. This is going to be pulling to the left at 5 newtons. And if you want to calculate the overall force acting on the object, well, you got to sub those two forces up. That'll be 5 newtons, negative 5 newtons plus 5 newtons. Well, that's just going to be 0 newtons. So the overall force acting on the weight scale will actually be 0. However, the reading on the weight scale will be 5 newtons. And I told you it's a really weird concept, but it works. It really does work. Okay, almost done. So Sam and Sally have the same mass. Sam and Sally work out together, but Sally is much stronger than Sam. So she does CrossFit and she's really super strong. But Sam he weighs the same as Sally, but he's not as strong as her. So they're on ice skates. Okay, bear with me. They're on ice skates, and they're going to begin reeling each other in. When they do that, where will they meet? Will they meet? Will Sam, if this is the midpoint, will Sam move over here? Or will will Sally move over to here, or will they meet in the middle? So will they meet in the middle? Will Sam move over to here, or will Sally move over to here? Now remember, Sally is twice as strong as Sam. Where do you think they will meet? All right, pause the video now. Okay, well, when they're pulling on each other, it doesn't matter who pulls. The force is going to be equal and opposite. Okay, so Sam is going to be pulling Sally, and Sally is going to be pulling Sam. Even though she's twice as strong, they have the same force. And since they have the same force, since they have the same mass and the same force, their acceleration vector, so Sally's acceleration vector, is going to be to the left. Sam's acceleration vector is going to be to the right. And those acceleration vectors are going to be exactly the same. Since the forces are equal, and since they both have the same mass, those two accelerations will be the same, which means they will meet right in the center. Okay? Whenever you emotionally accept this as a concept, just could you please email me or let me know? Because I am still not happy about that. All right. Now, same situation where Sam and Sally have the same mass. Sally just decides to give up. I'm going to tie a rope to myself, and now Sam is going to just pull. Where will they meet? Will they meet in the middle? Will Sam move over to here? Or will Sally move over to here? Which situation will happen if only Sam is pulling and Sally is not pulling? She's just tied the rope to herself. Go ahead and try this out and pause the video now. Okay. Well, again, Sam is pulling this way. Sally is pulling this way. Well, even though Sally is not pulling, forces are always equal and opposite. So those forces are the same, which means Sally's acceleration, as long as she has the same mass, she will begin accelerating towards Sam, and Sam will begin accelerating towards Sally. And since those forces are the same, they're always equal and opposite, that means the two accelerations will be the same. So again, they will meet right here in the middle. Okay. I think that's good enough. Well, actually, let's do this. Let's stop for today. Okay. Well, I hope you all learned quite a bit about Newton's three laws and how weird they truly are. Please do the reading if you haven't done the reading, because they do go in more depth there. And have a good day.